Welcome. My name is Carlos Villegas, and this is my final project in a class called Applied Cryptography. I chose my final project to be on something that I was curious about exploring, and so I did it on secure messaging with steganography. So, why did I choose secure messaging with steganography? Well, just think about it. A lot of people communicate with each other, and what better way to demonstrate cryptography is with sending a message, but not just in any encrypted way. You hide the encrypted message inside of a normal looking image. That to me had a certain appeal and that was challenging because I've never done anything like this. So this can be extended to in many ways, and I suggest some ways in the code that I plan to do in the future. But students that are starting in cryptography or enthusiasts that this project can use as a stepping stone for their future studies. And I've never done anything like this, so it seemed to be cool to do it. Interesting, very interesting. So let's look into what makes this application give the sender and the receiver confidence that their message is cryptographically secure and can withstand many types of attacks, like replay attacks, but more importantly, have the guarantee that the message has not been tampered with and it comes from the person who is sending it, that the receiver knows and is authentic. Users of my application can be certain that their message is protected against the most lethal kind of attack in cryptography, which is the chosen ciphertext attack. My application uses AES 256 in CBC mode. One of the things I've learned most in this course is that cryptography is nothing. It's useless unless you have good, solid, pseudo-random data. And I take every precaution necessary to make sure that my pseudo-random data is the best possible quality my hardware can produce. So I make sure that anywhere I use it, I properly seed it with time up to the microsecond level. So for this application, since I'm using AES, each time I encrypt a message sent by the sender, I properly produce an IV, an initialization vector that is good, solid pseudo-random data, along with a salt that is also pseudo-random data. These are the features and qualities that I've put in place to make sure that the message is cryptographically secure against the most lethal attack, which is the chosen ciphertext attack. This is the second most lethal attack. It's the chosen plaintext attack. And my application protects against it for the same reasons as the chosen ciphertext attack. Likewise against known plaintext attacks. So the last attack is the known ciphertext attack. And it's pretty benign because the attacker, the adversary, merely just has the ciphertext. But in my case, I hide the ciphertext in the image, so it's not obvious. So there's an extra layer of security that this is why it's also protected against this benign form of attack. The eavesdropper attack is an attack where the eavesdropper can guess which message you are sending. If you're sending two messages, he or she can guess. But because this application uses really good pseudo-random data, it's impossible for an eavesdropper to guess. So users of my application are protected against replay attacks, and they have the certainty that the message being received is not old, because I embed two defenses in here. One is the session tokens and another one is the timestamp, both of which are encapsulated in this piece of data that is sent. It's pickled and sent across the ports, and then unpickled on the other one, and it's cryptographically hashed on the sender side, so that when the receiver receives it, he or she can, or the application checks the signature and make sure that the information within has not been tampered with. We'll look at that a little bit in more detail. But we use two forms of defense against replay attacks. So this application defends against data modifications. So the people communicating are certain that their message and image have not been tampered with. I use something called a hash message authentication code, which is protected. It protects the integrity based on a trapdoor permutation, which has a secret shared password that each the receiver and the sender have, and that is used to encapsulate into this secure blob of data that even if one bit is changed, the receiver will know, and therefore the message will be dropped. Let's turn our attention now to a little bit of the internals of the application and the workflow. So let's get into the nuts and bolts. In the first bullet, I just want to formalize and say that I am using pseudo-random data, and I'm properly seeding it to the microsecond level. The next bullet, I am using two mechanisms to protect against replay attacks. Third one, I want to formalize and say that I am using AES 256 in CBC mode, which is a very strong encryption, and it's very popular because it works if it's done right. The next one, I take the encrypted message, in other words, the ciphertext, and I break it up into bits and sprinkle it throughout the image. Every time I encrypt a ciphertext, I salt it with 64 bits of random data, and the CBC mode of AES uses an initialization vector, which is 128 bits of pseudo-random data. I never use the master key, that is the shared secret password. I derive from it from a key derivation function, and I iterate about a little bit over 10,000 times to make it a little bit more secure. And finally, we seal the data in a cryptographic hash protected message, and we send that out. And here we have one of two slides dedicated to the workflow of this application. So we start on the extreme upper left hand side, and we work our way around from left to right, and then we drop in after the ciphertext. The ciphertext go into the Steganography engine along with the image that the user has selected, and finally a blob of data comes out, and it's the image along with the ciphertext. And you can see all the different stages and all the inputs along with the outputs. where the key derivation function is and the encryption algorithm used with it, which is AES 256. And in this slide, I wanted to emphasize that the receiver gets two pieces of data, independent from one each other, but they are related. And the first one is the image with the ciphertext embedded, and the second one is the HMAC, which is the HMAC message, along with all the different and very important pieces of information necessary to verify and guarantee that this message has not been tampered with and is authentic. I'm at the 10-minute marker right now, so I think it's time to show the application and see the encryption in action. My application has the following dependencies and prerequisites. In order to run the application, the server SMS has to be executed first. So here we see the command that starts the server, along with the screenshot and some initial log events that it produces at initialization. It's worth noting at the bottom in yellow text, that's the initial startup log, and we can see that the session token is computed by the server at initialization one time. From that point on, when the client connects to the server synchronizes the session token to the client. The client needs to start after the server. Here is the command to start the client, along with the initial screenshot and log events. So let's drill in to talk a little bit about the session token. The session token is something special. And if you think about it, these are the client and the server are two independent applications. They could be running next to each other on the same machine or on different machines across the world. And they need to share an initial very important piece of information at the beginning before any messages are exchanged, because the session token is part of the message used to ensure integrity and authenticity. And this slide captures what goes on in the server and the client in order to synchronize the session token. Okay, let's start with the demo. The server is on the left, the client is on the right. So initially we're going to send a message from the server to the client. So initially each user chooses an image, and then a shared secret password needs to be in place on both. And now the sender gets ready to type in the message. So once the message is typed in, and both sender and receiver have the same shared password, we are ready for the sender to hit the send button. So for each send, the receiver receives two pieces of data. The first one is the image with the ciphertext hidden within, and here's the log for that piece of data. So it received an image of a little bit over 0.5 megabyte. This is the image it received. This image has the ciphertext embedded within. Once the second message validates that everything is authentic, we get the message on the receiver side right there. Let's take a closer look at the actions that the receiver had to do in order to verify that everything was authentic and that the message was not tampered with. Let's look at the log for the receiver. Here's a glimpse at what the log looks like, but let me zoom in and show it to you line by line on what actually gets generated. So this second piece of data is the hash message authentication code. It's 554 bytes long. Right here we test to make sure that both shared secret passwords are synchronized. If they are, then we continue picking off all the important items within the HMAC message, such as the session token, the timestamp, the cryptographic hash of the image that was sent in the first block, the size of the image. If that passes, then we try to reassemble the bits from the hidden ciphertext. We decrypt the ciphertext, and if that's successful, then we display the message on the receiver side. So none of this would have been possible if the sender didn't do equally hard work. Let's take a look at that. Here's a brief view of the sender's log. Let's look at it in a little bit more detail. So the very first thing the sender tries to do is to encrypt the message and then hide it inside of the image. That's the steganography part of this application. And then it prepares the hash message authentication code with all the bits of pieces of information needed on the receiving end to guarantee authenticity and integrity. And that's all. Thank you for your time.